The Big Bang Theory is our best explanation of how the universe began. It's a story of incredible expansion from a tiny point. Imagine the entire universe squeezed into something smaller than an atom. That's the singularity, the starting point of everything we know. From that tiny point, the universe expanded rapidly. This wasn't an explosion in space, but rather an expansion of space itself. Think of it like a balloon being inflated, with galaxies like dots on its surface moving apart. The Big Bang Theory doesn't just tell us how the universe began. It explains the universe's evolution, from the first elements to the galaxies we see today. It's a journey through billions of years, all the way back to the very beginning of time and space. This theory is backed by a lot of scientific evidence. We observe the universe expanding and find remnants of the early universe, confirming the Big Bang as the leading explanation for our cosmic origins. The singularity is a mind-bending concept. Imagine all the matter and energy in the universe compressed into an infinitely small point. This point, smaller than an atom, had unimaginable density and temperature. We can't observe the singularity directly. It existed before the laws of physics as we know them. Time itself may have begun at the singularity, making it a difficult concept to grasp. Despite its mysterious nature, the singularity is a crucial part of the Big Bang Theory. It represents the ultimate starting point, the seed from which the entire universe emerged. While we may never fully understand the singularity, its existence helps explain the universe's incredible expansion and the formation of everything around us. The Big Bang wasn't an explosion in space, it was the expansion of space itself. Imagine baking bread. As the dough rises, raisins within it move farther apart. Similarly, galaxies move apart as the universe expands. This expansion started incredibly fast, much faster than the speed of light. This period, known as inflation, lasted for a tiny fraction of a second. During inflation, the universe grew exponentially in size. The expansion continues today, but at a slower rate. We know this because we observe distant galaxies moving away from us. The farther the galaxy, the faster it recedes, a key piece of evidence for the Big Bang. The universe's expansion is a fundamental aspect of the Big Bang Theory. It explains the distribution of galaxies, the cosmic microwave background radiation, and the evolution of the universe over time. In the first few minutes after the Big Bang, the universe was incredibly hot and dense. It was like a cosmic pressure cooker, where fundamental particles like quarks and leptons existed. As the universe cooled, these particles combined to form protons and neutrons, the building blocks of atoms. Protons and neutrons then came together to form the first atomic nuclei, primarily hydrogen and helium. This process, known as Big Bang nucleosynthesis, created the light elements that make up most of the universe today. About 75% hydrogen and 25% helium, with trace amounts of lithium and beryllium, were formed during this early phase. The abundance of these light elements in the universe is strong evidence for the Big Bang Theory. The predicted ratios of hydrogen and helium match observations supporting the idea of a hot, dense early universe. Section 5. From Soup to Structure. How the universe cools down. After the formation of light elements, the universe continued to expand and cool. As temperatures dropped, the universe transitioned from a hot, opaque plasma to a cooler, more transparent state. Around 380,000 years after the Big Bang, neutral atoms formed as electrons combined with atomic nuclei. This event, called recombination, marked a crucial turning point in the universe's evolution. Before recombination, photons, which are particles of light, were constantly scattered by free electrons, making the universe opaque. After recombination, photons could travel freely, and the universe became transparent. This transition allowed the universe to cool further and set the stage for the formation of larger structures like stars and galaxies. The cosmic microwave background radiation, a faint afterglow of the Big Bang, originates from this era. Section 6. Stellar nurseries, gravity's crucial role in star formation. As the universe continued to expand and cool, gravity began to play a crucial role in shaping its structure. Slight variations in density, present since the Big Bang, acted as seeds for gravitational collapse. These denser regions attracted more matter, pulling in gas and dust over millions of years. As these clouds collapsed, they heated up and became denser, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. This ignition marked the birth of stars. Stars are giant balls of plasma held together by gravity. They generate energy through nuclear fusion in their cores, converting hydrogen into helium and releasing vast amounts of energy. The formation of stars marked a significant step in the universe's evolution. Stars not only illuminate the cosmos but also create heavier elements within their cores, enriching the universe with the building blocks of planets and life. Section 7. Galaxies assemble islands in the cosmic ocean. Stars didn't form in isolation. Gravity continued to draw matter together, leading to the formation of larger structures called galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter bound together by gravity. The early universe was filled with small, irregular proto-galaxies. Over time, these proto-galaxies merged and interacted, their gravity pulling them together into larger and more organized structures. Our own Milky Way galaxy is a spiral galaxy, with a central bulge, a flat disk, and spiral arms. It contains billions of stars, including our Sun, and is just one of trillions of galaxies in the observable universe. Galaxies are not randomly scattered throughout space. They are organized into clusters and superclusters, forming a vast cosmic web that stretches across the universe. Section 8. Evidence for the Big Bang echoes of the early universe. The Big Bang theory isn't just a compelling story, it's supported by a wealth of scientific evidence. One of the most compelling pieces of evidence is the cosmic microwave background radiation, or CMB. The CMB is a faint afterglow of the Big Bang, a snapshot of the universe as it existed around 380,000 years after the Big Bang. It's a faint glow of microwave radiation that permeates all of space. The CMB was discovered accidentally in 1964 and provided strong evidence for the Big Bang theory. The temperature and uniformity of the CMB match predictions from the Big Bang model, supporting the idea of a hot, dense early universe. Studying the CMB allows scientists to probe the early universe and learn about its conditions shortly after the Big Bang. It's a treasure trove of information about the universe's origins. Section 9. Redshift and expansion galaxies moving apart. Another crucial piece of evidence for the Big Bang is the redshift of distant galaxies. Redshift is the stretching of light waves as they travel through space. As a light source moves away from an observer, its light waves are stretched, making the light appear redder. Astronomers have observed that the farther away a galaxy is, the more redshifted its light is. This observation indicates that distant galaxies are moving away from us, and the farther they are, the faster they are receding. This redshift distance relationship is exactly what we would expect to see in an expanding universe. It's like dots on a balloon moving farther apart as the balloon inflates. The redshift of galaxies provides strong evidence for the Big Bang theory and supports the idea that the universe is expanding. By measuring the redshift of galaxies, astronomers can estimate the universe's expansion rate and its age. Section 10. The future of the universe, expansion, dark energy, and beyond. The Big Bang theory not only explains the universe's past but also provides insights into its future. The universe's expansion is accelerating, driven by a mysterious force called dark energy. Dark energy is thought to make up about 70% of the universe's total energy density. Its nature and origin are still unknown, but its effects are profound, causing the expansion of the universe to speed up. The accelerating expansion has implications for the universe's fate. In a scenario known as the Big Freeze, the universe will continue to expand indefinitely, becoming colder and more diffuse over time. Galaxies will move farther apart, and star formation will eventually cease. However, other possibilities exist, such as the Big Rip, where dark energy's influence grows stronger, eventually tearing apart galaxies, stars, and even atoms. The ultimate fate of the universe remains an active area of research. Section 11. Conclusion, the Big Bang and our place in the cosmos. The Big Bang theory is a remarkable achievement of modern science. It provides a comprehensive explanation for the universe's origins, evolution, and future, supported by a wealth of observational evidence. From the initial singularity to the formation of stars and galaxies, the Big Bang theory tells a story of incredible transformation and complexity. It reveals a universe that is constantly expanding, evolving, and full of mystery. Understanding the Big Bang allows us to appreciate our place in the cosmos. We are part of a vast and ancient universe, connected to everything around us by the fabric of space and time. The Big Bang Theory is not a final answer, but rather a starting point for further exploration and discovery. As we continue to study the universe, we can expect to refine our understanding of the Big Bang and uncover even more about the nature of reality itself.